Okay, so now it's recording. And you can see the screen, right?
Yes.
So you have a vector field, and that means you have assigned one vector from these vector spaces at different point, at each point, and you want to have some idea how this vector field is changing. So essentially you want to define some kind of a derivative. And you will do it typically along some curve, that as you move on that curve, what is the rate of change of this vector field. So you are trying to compute something like that. It's a proper vector assigned at each point, and you are computing its rate of change. So this you can write. Yeah, everyone has to mute their things. अ, आप लोग म्यूट कर देना अपना. So how do I mute everyone? Security. I don't see it anyway. So this d by d beta, I was expecting it to be something like this. But this naive derivative, which is just like you're looking at that how the components change from point to point, that doesn't do the job. That doesn't mean much. And one problem with it is that it doesn't give me a tensor. I want this, that I have made a difference of two vectors. I expect it to be a vector back again. Using naive derivative, partial derivative doesn't do that. It doesn't give me back a vector, and it shouldn't, because I don't know which vector over here connects to this vector at the next point. So the idea was that I write something like this, and this is defined in this way, that I can act on just the components so that it's easy to see that what's going on. It tells me how the components in any given basis connect to the components at nearby points along a curve. That's the whole idea of this covariant derivative. I write it like this, but when it acts only on the components, leaving aside, because it's defined at one point. So it tells me how the components have to be compared at nearby points in one particular basis. And what do we want from it? We said that we want this to be linear, and number two, should obey Leibniz rule, which means if I have two of these, it should be like this. And well, before this, I should say that I should be defining it define for all tensors. That means that if I have a tensor field T, I want to know how it changes as I move along a curve beta. So it would be just given by this thing. I should know what is the action of this covariant derivative on any tensor field. And in particular, I want this to have for this thing to give me back a vector. I want for this to be a vector. I want this thing to be a 1-1 tensor, so that when I do this, then this is contracted index. So this transform with something like this, and this transform in the opposite way, so they cancel, and this guy then becomes a proper vector. So this will happen if I assume that d mu v alpha is a 1-1 tensor. Actually, this was the main problem, that this guy is not a 1-1 tensor because does not transform properly.
Sir, d mu v होना चाहिए ना, ये सिर्फ components काम से रिलेटेड. D mu v should be a 1-1 tensor.
D mu v alpha is a 1-1 tensor because it's an indexed object. If I just write dv, that means it's a
D mu v.
no. You can say this thing: dv is a 1-1 tensor, and d mu v alpha are components of a 1-1 tensor. That's what you mean. The d mu v alpha should give you components of a 1-1 tensor, so it transforms properly. And in general, this d mu, what it does, or this d, what it does when it acts on a tensor field T, it transforms. It takes a m by n field to a m n plus 1 tensor. That's what it do. So it should be linear, should satisfy Leibniz rule, and it should give you back a tensor with an added extra index. And we said that we will construct it, since we want it to be linear and have a kind of a Leibniz rule. So we guess, or not guess, we just define it this way. That this would be, we add this kind of correction and then demand that our constructed object have the properties which we expect it to have. So just because I have taken it to be linear, those two things, that it's linear and it satisfies the Leibniz rule, they will be satisfied automatically. All I need to do is make sure that it satisfies the other thing, that it has to d mu, let's say number 3, demand that d mu v alpha transforms properly. By properly, I mean like a 1-1 tensor. And we had argued, you should definitely go back, look in the notes, we had argued this thing from the perspective of, if I bring a nearby tensor field back and connect it to this, that how it should look over here, and try to form a derivative, then again, up to first order, I said that I should get some linear combination of the components over here. So you can argue this form, that is a reasonable form for a covariant derivative from that perspective as well. Let me not repeat that over here, but you should definitely go and look in the notes. We discussed it in much detail last time. So this is what we want. That means we want d alpha v mu to be transforming like this. Like this. But the first part of it, which is d alpha v mu, This doesn't. This we know goes like this. Mu dash plus it has this non-homogeneous term. Something like this. So we don't want this. So we can cancel it against if we demand a proper transformation of this. So require that this guy, this has a piece mu dash v beta well, if you want, you can put primes over here minus the opposite of what you had over there. So that's all you need. So pick up some combination, some numbers, gamma, mu, alpha, beta. Well, actually, these will be a kind of a field because you have to define it at every point because you are going to construct this. You have to tell that how does this derivative looks like at every point. It gives you the rate of change along a curve, but it's defined at every point. You give it a curve, it tells you how does the field changes if you go in that direction, but it's defined at every point. So you have to give these numbers, these gammas at every point, this set of numbers, and do not require them to be tensors. They should not be tensors, rather they should transform in this particular way so that the transformation cancels the non-homogeneous piece from the other thing, from coming from the partials. So this I can write, if I include this change, I can write it this way. Over dx beta beta dash tilde. So this comes from here, and this I want to cancel with I have a beta dash here, beta dash here, beta here. So let's keep this as beta. So yeah, so now this has a proper transformation between primed index from the left side and primed index on the right hand side and unprimed from the left hand side. I have just included that how the vector is going to change. So I have separated out the vectors transformation. And similarly, I may be screwing up some indices, but you should just go. It's actually part of your current homework. Do this transformation properly. I'm just doing it quickly. So I have just included the transformation of the vectors, separated them out. So I can pick up this piece. This will be then the transformation of the these connections. Connection components. Tx mu. And this guy, this second part does not have any connection components appearing, multiplying. So it's a non-homogeneous part. Something like this. We wouldn't need it much, but just this is extremely important to know that these guys do not transform like a tensor. So it's not a tensor. And the idea is that pick up any field which transforms like this. Pick up, so you can just define it in one coordinate system. You can define a covariant derivative by picking up the set of these connection coefficients at each point in one frame, and then demand that in other frames, how do you get them? By this transformation. Once you have done it, you have got a perfectly legitimate covariant derivative. It transforms like a 1-1 tensor, and it gives you one way of how to compute derivatives, how to connect different vectors at different points. And it's up to you how you want to define. Different definitions give you sort of different geometry. Different definitions tell you that which vector, like you should literally think of it this way, that if you have these two vectors, I kind of turn my sheet of paper, then this points in some other way. And I'm calling that this is the same vector as this, because this turning is happening because of the curvature in my surface. So how do you curve your sheet? It connects this vector to different vectors. And this choice of connecting these vectors with each other is the choice of choosing different covariant derivatives. And this is also the choice of defining a geometry or choosing these connection coefficients. Well, I had been writing them with a tilde above. So let me just put that in. Yeah. So once you have defined it, you can now compute. If you have a curve, you have a vector field. So you are given the components of this vector field in whatever coordinate system you are working in at each point. Then you compute this. This is the derivative of the vector field. Components of the derivative of your vector field. So it defines the rate of change of V along a curve, and it is still a vector because this is truly a 1-1 tensor, and this contraction removes one index. So you get back a 1-0 tensor, which is a vector. Gamma path pe nahi depend karta. Gamma is a vector field. Not a vector field, it's a field. It's defined at each point. This is the whole point, that you are saying that I want to define it in this way, that this object by itself, it exists at a point, d alpha v mu. It's defined at a point. And it's not defined with reference to any path. But once you contract it with so this guy, this is also a vector, this is also a kind of a field along a path, but along a path. So this T alpha beta is the tangent vector of this path, like this. And this guy is this vector field. which is defined at every point, but right now you're looking at it on the path. So you can also parameterize it with the beta. So this guy is actually, in some sense, giving the components of this guy this rate of change, but properly computed. So the prescription is do it this way. So it computes for you rate of change of, this is rate of change of the vector field along this curve. Which curve? Whose tangent vector are these guys. Now, if you put this equal to 0, then you say that the field V mu is being parallelly, this vector field is being parallelly transported along this curve. Because this equation is saying that as you go along this curve, there's no change in this vector field. So that means the vector, in a sense, you are keeping the vector parallel to itself. You're not changing its direction or changing its length, but that's not much important. You're not swirling it around. It's keeping it as straight as you can. So this equation tells you how to parallelly transport a vector. And this depends on path. And how do you solve it? How do you find this parallel transport? You have to actually find a field. You're given a path, and then you look for a field which is covariantly constant. So find, this is another terminology for it, covariantly constant vector field. That means its covariant derivative is 0 along this path. It may be 0 along this path, but this vector field is set up in the whole region. So it may be true that you go from here to here. There's only a unique vector defined at this point. And along this path, you conclude that its rate of change was 0. But you take another path and you follow this vector field, you will end up with the same vector because it's uniquely defined at each point. But it may be true that along this path, this vector field is not covariantly constant. So this may not be covariantly constant over here. Along a different path. So इसका एग्जांपल हमने वैसे लास्ट टाइम किया भी था कि if we are on a sphere, a field which is like this on the equator and it has other values at other places is covariantly constant because you are trying to find parallel vectors in the 3D and then you project them onto the tangent space at that point. So you will just slide over here. But if I take this path, which field would be covariantly constant along this path? It would be this one, which goes like this. Because if you again imagine you're keeping this vector parallel in the 3D, and then you keep projecting onto the sphere. So you end up with a vector pointing in this direction. But this field, if I smoothly define it, I have to fill it somehow over here. I can probably fill it like this, turn it slowly, and fill it like this, so that I end up with this same vector. This is not covariantly constant along this path. The field which is covariantly constant along this path goes like this. Well, maybe this color goes like this, because it is keeps parallel with this while you project onto it. And this will give you a different vector over here. So parallel transport along different paths may end you up with different vectors at same point. So they will correspond to different vector fields, not the same one. Hmm. Hmm. नहीं, so this is the vector field पता नहीं होना चाहिए. You are finding a vector field. So when you say okay, I'm parallelly transporting this vector, so essentially you are solving a differential equation which gives you a vector field, but it only defines it along that path. Baki rest of it you can fill as you want. This equation will only give you a vector. It will only define it along that path. So it's only being careful when you say that I'm finding a vector field. But usually, colloquially, people just say, let's parallelly transport it along this path. So they just solve this equation, and you are just finding out that as you go along this path, how does this vector, which vector you have to pick up at each point. So that's essentially finding a field. So you can say that I start with this vector, let's parallelly transport it along this and this line. And your equations will tell you that you get this vector. Path agar fix kar dein, then you will get a fixed vector at the end by solving this equation, this one. This is equation of parallel transport. So now you want some other conditions. So this is for so far what we have done is all about vectors, but we want to define it on arbitrary tensors. So you keep going and you want to define something derivative of a one form. Or maybe the right terminology should be action of covariant derivative on a one form. So again, one forms are not very different from vectors. They just have a lower index. They're just a dual space. So everything, all the arguments which I have made before, you use the same arguments and similarly define that this guy should be now a 0-2 tensor. That's all you want from it. And a partial does not transform properly. Again, you want linearity and Leibniz rule, all those things, and this thing to transform properly. So you will have this kind of index structure just from linearity. You will want to include a vector component in these with these coefficients. So you have to contract those components like this and leave mu and alpha two new indices so that the indices match on both sides. You can think of it that way. What happened? I hope the internet is not gone. No. Well, you can kind of think of it that way as well. Now we put another condition. So I don't know, I'm not keeping track of the conditions. Probably it's the fourth. You demand that the covariant derivative of a number, of a scalar, derivative of a scalar is just a partial derivative. Because what else it could be? Because on scalars, we know that the partials, these guys, they are already tensors. Because nothing comes from within, this transforms like by chain rule, this just transforms like this, which is already a proper one-form transformation law. So a scalar is a 0, 0 tensor, and it's mapped to a 0, 1 tensor just by the partial. So the partial acts like a covariant derivative on the scalars. So that means you want, if I compute this contraction is a scalar field because at each point you are computing a number. So this should be just this W alpha plus V alpha like that. But now I use, because I have already demanded that I should have a Liveness rule. So on this side, I can use the Liveness rule. W alpha W alpha like this. So over here, it becomes just a partial. But here I can now start using my formulas. V alpha plus alpha mu beta V beta W alpha, right? Plus I should have a W alpha here as well. Plus on the other guy, so it's V alpha D mu W alpha plus. So the idea is that I'm saying there will be some other coefficients for the one form, which I'm writing with the double tilde. And the structure should be this, because I have to contract with this, and this contracts with V alpha. Right? Because when I'm doing the vector index comes onto the connection coefficients. ये V alpha था, ये V alpha में चला गया. Similarly, the one form index comes down into the connection coefficient, or वन फॉर्म का जो ऊपर वाला इंडेक्स है वो मैं वन फॉर्म का जो अपना नीचे वाला इंडेक्स है वो मैं इसके कनेक्शन के ऊपर वाले इंडेक्स के साथ कंट्रैक्ट कर रहा हूँ। सिमिलरली वेक्टर में वेक्टर के ऊपर एक इंडेक्स होता है वो मैं नीचे वाले के साथ कंट्रैक्ट कर रहा हूँ, लाइक बेटा एंड बेटा एंड बेटा एंड बेटा. But then, because I was contracting these one forms with the vectors, तो ये अल्फा इस W अल्फा के साथ कंट्रैक्ट हो गया क्योंकि वेक्टर इंडेक्स इसके ऊपर चला गया था, इसके साथ कंट्रैक्ट हो गया. सिमिलरली ये जो है ये वन फॉर्म का इंडेक्स है, ये वेक्टर के इंडेक्स के साथ कंट्रैक्ट हो गया. Now these guys, these partials, इनको मैं कंबाइन ऐसे लिख सकता हूँ. So they will mu beta v beta w alpha plus alpha mu beta v beta w alpha. I have just in the second term I have just replaced betas with alphas so that these two guys they look same. Now they are same, so this should be 0. So for these to cancel, I have to have alpha mu beta is equal to minus alpha mu beta. So the connection coefficients which are defined for the one form, they have to be equal to the negative of the connection coefficient for the vectors. So I don't need to even define them. They're just given by the vector coefficients and the connection coefficients of the vectors. So I just define this double tilde. I just demand this. I just define it this way. And this is equal to minus. So just only define these guys and then define these two equations. Like this. Then you can keep going. So this gives you that if you have this covariant derivative dotted with t, this just means d mu along some path. So if I define it on this action, this I'm again writing that law v mu d by dx mu tensor this will be the Liveness rule, and it just tells you v mu plus W alpha dx mu d by dx alpha. So this is the like a basis for 1, 1. You can take it out, and this is exactly the Leibniz rule which I had used above. So just writing it more carefully. But writing it this way, it gives you can then generalize it. That if you are given any tensor, for example, any object. So for example, if you're given an object like this, its covariant derivative using the same logic which I have done above over here, कि एक दफा आपने basically आपने अपना Leibniz rule use करना. So it would be gamma mu alpha sigma. एक दफा आप पहले इंडेक्स को रिप्लेस कर देंगे, एक दफा आप दूसरे इंडेक्स को रिप्लेस कर देंगे. म्यू बेटा ए अल्फा सिग्मा. Similarly, अगर मैंने ये लिखना है, I have an object like this, so it would be d mu of a alpha beta plus, when I act on the vector index, I put a plus. Mu यहाँ से करना है और सिग्मा ये जो वेक्टर इंडेक्स है वो सम हो जाएगा. Then you write it for the one form index. तो वन फॉर्म इंडेक्स के लिए करना है तो एक म्यू आएगा, ये यहाँ से डेरिवेटिव इंडेक्स है, एक बेटा आएगा और वन फॉर्म इंडेक्स आपने अब सम करना है. Like this. This is just the use of the Leibniz rule in a nested way. Well, not really nested way. वहाँ पे 1, 1 के लिए किया था, यहाँ पे मैंने यही वही 1, 1 है, ये मैंने 0, 2 के लिए करके दिखा दिया. Similarly, you can keep going. And you can use it in a nested way to derive that for each one form index, you put a minus sign and sum over the one form, remove the one form index and sum over it. Similarly, for each vector index, you put a plus sign and remove the vector index and sum over it. So you can just keep continue doing it. So it, in a sense, so that means once you give the coefficients of the vector, the connection coefficients for the vectors, it's done for all tensor fields. You have defined the covariant derivative and its action on all tensor fields. Now I'm going to put a few more conditions, but to discuss the next condition, first we need to discuss this thing, torsion. Maybe at some point in next course we will discuss what does it physically mean, but algebraically it's something very simple. So I said that you can define any set of these coefficients. As long as they transform properly, they are a connection coefficients. Suppose we have two different connections. So given these coefficients is called giving a connection. So you are given two connections. Gamma tilde and gamma tilde hat. Then if I compute this guy, and this guy, covariant derivative computed with the first set of coefficients minus covariant derivative computed with the second set of coefficients. This transforms like a 1-1 tensor. This transforms like a 1-1 tensor as well, because this is also a legitimate covariant derivative. It has properly transforming connection coefficients. So I'm taking a difference of two 1-1 tensors, so I must get a 1-1 tensor back. But when I compute this difference, the partials will just drop out. And I'll be left with lambda mu nu so vector index is summed by introducing a new dummy variable. So that means this guy is a true tensor. It has a structure like this. So if I'm giving it a 1-0 tensor, so this 1 is eaten up by one index over here to give you a 1-1 tensor. So this means I can define this guy this will be a true tensor. This means difference of any two connection coefficients is a tensor. They are not tensors themselves, but if you make a difference, then they're tensor, because it so happens that because it's kind of obvious, because in their transformation law, they have a non-homogeneous piece, which doesn't care about what are the coefficients themselves. It just cares about the indices. So since you are making a difference, so those non-homogeneous pieces, they just drop and you get a tensor. So let me go back over here. Where was the transformation law? Yeah, over here. So you can see these coefficients do not even appear over here. So if I write it for one kind of coefficients or another kind, this is same. So it's gonna cancel out between two, and I will have a tensor if I take a difference. But now if I have a set of, I have a connection given by these, then so is these. So if I replace the lower indices, exchange them, so exchange the coefficients. So like, for example, if I have 1, 2, 3, I say in the new connection, this is same as, well, in the new connection, lambda 1, gamma 132 is same as gamma 123 in my old connection. This will also be a connection because transforms properly. Why does it transform properly? We can go back up. This transformation law is not written very properly because I had to have another one over here. But in any case, I think what will happen is you will have a beta dash here and you will have another one gamma x beta dash over here. But you can work it out and see that it doesn't matter. If I switch mu nu by nu mu in this transformation law, nothing changes. Nothing changes. So if you exchange those two, you still have the same transformation. And this guy also defines a connection. So if they are both connection, then I can define a new tensor. It's called, so let's call it T lambda mu nu, and define it by take your connection, flip the indices, and take a difference. Since they're both connections, this is a tensor. And it's called the T lambda mu nu is the torsion of this connection. So given a connection, you can compute its torsion. It's a tensor. Now, if I demand, this would be my fifth demand. I demand that my connection is torsion free. That would mean we are keeping the symmetric part of the connection coefficients. So remember this thing. So torsion free, for first of all, for this to be torsion free, you want this to be 0. This means your connection should be symmetric. So a torsion free connection is symmetric in lower indices. And you can think of it that starting with any coefficients, because any indexed object, we can write it as a symmetric plus antisymmetric part. So you are putting this equal to 0 and only keeping the symmetric part. Or in other words, if you choose your coefficients in such a way, and you can do it, that it's symmetric in its lower two indices, then this kind of connection would be called torsion free. You definitely have geometries. You can define geometries which have torsion. And even in gravity theory, people play with these torsion full geometries, but Einstein's gravity and much of the sensible geometries which you consider are torsion free. Definitely Einstein's gravity is based on a torsion free geometry. So we will demand this. The last thing which we want is metric compatibility. So what is metric compatibility? So suppose you're given a curve, and you have defined a metric in your space. Defining a metric in your space means at each point you're picking a metric, right? So you have defined a metric field. What does that mean? That means you have a symmetric 0 to tensor selected at each tangent space. You've already done this job. You have selected this guy at each point. And you can select it by giving giving components in one coordinate system. If it doesn't cover the whole space, you have to choose many coordinate system, and so that you have defined it at each point, and then you know how to go from one coordinate to the other. So you have defined it, a metric, it exists in your space, and you consider if you have the metric and you take two vectors at a point, you can compute the scalar product. So scalar product is just the contraction. Let's call these vectors v and w. This would be the scalar product. Now suppose that these vectors are being parallelly transported along a curve. So when you parallelly transport them, this guy goes here, and this guy goes like this. So suppose you further demand that when you parallelly transport two vectors along any curve, not one curve, along any curve, then your connection coefficients should be such that the scalar product should not change. So suppose V and W are parallelly transported along a curve. It's colloquial language. It essentially means you have defined a field which is covariantly constant along this curve. So let me write it out. This means they are being parallelly transported. That means for this curve, this is true and this is true. If they are being parallelly transported, then the scalar product along this curve should be preserved. This should be 0. So how do I write? This is a number. So this is just an ordinary thing, but I should be able to use my Liveness rule. So I get T alpha D alpha G mu nu plus T alpha G mu nu comes outside. T alpha D alpha V mu W nu. Let me put this thing like this. Doesn't matter. T alpha D alpha W nu. But since they are being parallelly transported, so this guy is 0 because V is being parallelly transported, and this guy is 0 because W is being parallelly transported. So if this thing has to be 0, This means we must have because it holds for all curves. We will demand it that the scalar product should be preserved along all curves. So this condition that the covariant derivative of metric should be 0 is the metric compatibility. Now we don't know if we can at this point we don't know if we can always select such components. Like if I give you any arbitrary metric, can you find components so that this would be true? So that's our next problem. But before we go there, notice that this metric compatibility has many nice properties. Well, first of all, scalar product will be preserved. Of two parallelly transported vectors if metric compatible. एक second channel. So first of all, scalar products will be preserved, but it has many nice algebraic properties. Like for example, if you are doing this thing, you are contracting some tensors like this. So A and V are being contracted. So because of metric compatibility, I can freely, because remember when you have contraction, you can lower the index of one and raise the one of the other. You can still do it inside the derivative because the ho kya raha hai, when you have a contraction, you have a metric over there. So that metric, it just goes freely in and out of the derivative because in the Liveness rule, it's just a constant. So you can do this so that this d alpha truly acts. Well, first of all, we will be able to freely raise and lower indices inside a covariant derivative. And this d alpha acts as a tensor itself. So this symbol, I should say not d alpha, this derivative symbol acts just like a tensorial object. Because you can take things in and out and it doesn't really matter. Now I want to study if I can really find such a connection which will be metric compatible. Should we take a break? क्यों आज क्या double नहीं तो थोड़ा सा तो or should we just finish it? कंटिन्यू कर लें. Okay. So this is called what I said I'm going to prove. This is also called Levy Civita connection. You can think of it as a consequence of metric compatibility. So suppose you are given a metric field and you want to define a metric compatible. You want to define a connection which is compatible with this metric and also torsion free. Connection. So if this exists, this would be called the Levy-Civita connection. And we don't know, I mean, there may be many of these. So do they exist? And how many? Well, let's start. Now this is going to be a little bit tough because we have to keep a track of symbols. So I write this meter compatibility condition. It is this gamma alpha. I have to mu nu g. So the nu of the g came into the Christoffel, and instead of when I removed that nu, I replaced it with the summed index alpha, and the second just remained like that. And the second time, again you have a summed index, and again you start with mu, one mu coming from the derivative, and then you put in the index which you remove from the one form index of the G. So once you remove the nu, which came in under inside as an index of the connection, and now you are removing the rho, right? So nu alpha. So is this clear? I hope this is now clear how to write this derivative. And this you are putting equal to 0. Now the thing is that this equation can be, in a sense, algebraically solved by just a permutation of indices. So now I slide these cyclically. So bring nu here, rho here, and slide this mu and bring to the other side. Now I will ask you to just check that I am doing it correctly. Gamma alpha, nu comes here, rho comes here, and mu is slided over there. Is this okay? Because I replaced mu by nu, rho by mu, so that's okay, and nu by rho. I'm just comparing over here, nu by rho. So this is fine. Over here, I have to replace mu by nu, rho by mu, and nu by rho. Fine. Now I do it once more. I slide them again. G rho G mu nu. G rho G mu nu. So nu goes to rho. Rho goes to mu. And mu goes to nu. So nu goes to rho, mu goes to nu, and rho goes to mu. Now I just subtract second and third from first. And if I've done things correctly, something nice will happen. And I have to remember, because I'm using the property that it's torsion free, I have to remember these are symmetric, and so are G's, because metric is symmetric in its indices, and the connection, torsion free connection, is symmetric in its lower indices. So what do I see? I have mu rho alpha nu. So this guy goes with this, and I'm subtracting, so they are cancelled. Mu nu rho alpha, right? I can exchange this mu nu and this mu nu, nothing happens, and rho alpha. So this guy marked with 2 goes with this. And so I'm left with this equation. D mu G nu rho minus D nu G nu mu minus D rho G mu nu, and I have a plus gamma alpha nu rho, and plus gamma alpha nu rho, because they are same. Let me write it: rho nu G mu alpha is 0. So that means now I can separate out this guy. This is 2 times. There were 2. I can separate this guy out by multiplying with an inverse metric. And I will have a formula for these coefficients, which are metric compatible, because that's the condition I used, and which are torsion free in terms of G's. So given the G's, I can compute these. They will be uniquely determined. First of all, they will exist if I have defined G, and they will be unique. So there will be a unique metric compatible torsion free connection, which will be defined once you are given the metric. So in this sense, although the geometry is defined through connections, but a metric compatible connection is defined once you are given the metric. So metric defines for you all the geometry you need. So we can just try to do it now. So what do you get? You get G mu alpha gamma alpha rho nu is equal to half, इनको अगर मैं उस साइड पे ले जाऊं, d nu g rho mu minus plus d rho g mu nu minus d mu g nu rho. So I multiply with beta mu g beta mu. This is g And this gives me a delta of beta and alpha. So this alpha is replaced by beta. And these are, I'm just copying. Now let me just look at this guy, that what is the structure? And let me replace these in a more slightly. So whatever is the upper index comes over here. And then you have a summed index. This mu is being summed. So I'm, well, let me write it mu. The upper index as mu. And summed index as sigma. Then you have this lower index coming in derivative. So I'm writing is at alpha like this, rho coming in derivative, and the sum index going into the metric. So sigma beta plus then the sum index, the other index of the connection coming into the derivative, and the sum index going into the metric alpha sigma. Then the minus guy comes where you put the summed index on the derivative. So these are the Levy-Civita coefficients, Levy-Civita connection coefficients. Which are defined uniquely in terms of the metric. And well, it's just about terminology, what people want to call what is Riemann geometry. But traditionally, Riemann geometry is this kind of geometry, which is defined through metric. So in terms of Levi-Civita coefficients, you give a metric and then you compute everything from the metric. But it's not the most general geometry. You can have more general where you do not want metric compatibility, or maybe you want metric compatibility, but you do not demand torsion free. So you can have slightly more general geometries, but we will not concern them, at least for now. But if you recall this is exactly what we were calling Christoffel symbols. So Christoffel symbols are just the Levi-Civita connections. So people call them anything they like, Christoffels or Levi-Civita. There's one issue. I define the way I define the geodesic equation. I put them on the other side of the equation, while now most of the people write it on this side. And the way I have defined the covariant derivative, I should be writing the way I will define the what do you call geodesic equation. Those Christoffel symbols are just related to these with a minus, but I'll just change my definition of the geodesic equation and just use these. वो जो मैंने फॉर्मूला लिखा था उसमें I was putting plus here and minus here, but let's just use these from now on. Now for parallel transport, once you have agreed that these are the coefficients which we will use, a vector field V alpha would be parallelly transported along T mu if this is true. So if I open it up, it looks like this. Is 0 and T mu is this guy. These are the partials. So this just becomes d by d beta along your curve. And then you are dotting. This contraction is also called dotting the tangent vector of the curve and the vector field into your Christoffels. So you set up, you're given a curve, you set up this equation, and this is a equation, first order differential equation in the betas. These gamma alpha mu nu you will pick from their values along this curve. So it's a first order differential equation in beta, and given an initial condition over here, it will uniquely tell you that what vector field you should be setting up to get over here to get a parallelly transported vector along this curve. So given a curve, starting with a vector, you get a unique answer, how to parallelly transport a curve. Now, using this idea of geometry, how to connect nearby vectors, we can define a straight line. This time, we are not defining it using any concept of a distance. This is the smallest line or smallest curve or largest curve, nothing like that. You're defining a straightest possible line. So one that keeps straight, what could that mean? A line whose tangent vector always points in the same direction. So straight line वैसे क्या होती है? If I'm just in the straight in the flat geometry, this is not a straight line because ये जो tangent vector है और यहाँ पे जो tangent vector है, they're not pointing in the same direction. They have changed. So it's not the same vector. This vector over here is not parallel to this. This is straight because tangent vector at each point is parallel to the others. So they keep in the same direction. So you can say that a line is straight if the tangent vector is parallelly transported along the line. So you have already set up a field because it's the field of the tangent vectors along the line. And you are just checking if this field is the one which is being parallelly transported along the line, along the curve. So if it is, then it would be a straight line or it would be a geodesic. So this definition of geodesic is not in terms of any shortest length, but it turns out it's same. So it's kind of a proof that straight lines have the shortest, or at least maximal distance. So this is what you want. You are given this vector field T alpha, and you are parallelly transporting it along the same curve whose tangent vector is T. And this has to be 0. This is the geodesic equation. When I open it up, I get dx mu over d beta d by dx mu of dx alpha over d beta plus dx mu over d beta gamma alpha mu beta beta की जगह कुछ और यूज कर लें न्यू टी न्यू मैंने डालना ना तो टी न्यू की जगह मैं डी एक्स न्यू ओवर टी बेटा दिस इज द इक्वेशन यहाँ पे आई कैन यूज द चेन रूल so I get d beta square plus gamma alpha mu nu dx mu over d beta dx nu over d beta. So this is exactly the geodesic equation, except I think I was writing it on the other side. I was putting an equality over here, which is just changing the definition of the gammas with a negative sign. But let's use these. And this, with this, जो हमने पीछे expression derive किया, that's the correct expression. Now we can also understand why this holds true only in a only for very specific parameterization, only for what we call the affine parameterization. Why is that the case? Well, this condition may be too strong, because maybe all we want is this, that when you take the derivative of a tangent vector along this curve, then you should get a vector pointing in the same direction. So you may not be that I'm using different parameters. I'm using a parameter. तो यहाँ पे वेक्टर छोटा हो सकता है, यहाँ पे लंबा हो सकता है, छोटा लंबा, but that still defines the same straight line. But when I'll take a derivative over here, I'll get something non-zero, unless the length in some sense is also kept constant. So when I was putting it equal to 0, I was demanding that as I go from one point to another, I identify the vectors exactly. But that may be too strong for a line, for the definition of a line with arbitrary parameterization. So all I demand that when I subtract these two vectors, I get a vector pointing in the same direction. So it should be a multiple of the same vector. So this is a bit slightly more generalized geodesic equation. This is more generalized geodesic equation. So this would be everything same except you put it equal to some constant time, this vector. Doesn't matter what constant appears here, as long as this happens, it's a straight line. In fact, from the original equation, from original geodesic equation, if you put tau equal to some beta, then what will you have? If I change this parameterization, this is just chain rule. So this guy becomes यहाँ पे वही है. So when I open it up, I have dx alpha over d tau square times this guy, when this x on this, and they're just multiplied, but I have the other term, dx alpha over d tau and d2 tau over d tau d beta, but using the chain rule, I can change it to this. And then these guys have just this thing. So I can divide by this. I'll have a I will have an inverse of this over here. But whatever this is a constant over here. Well, constant in the sense it can change from point to point. So I can take it to the other side and I generate the more generalized geodesic equation. So if you're given the parameterization for a curve, you better check this because it may not be a fine parameterization. But if you are asked that construct a straight line, then you can start from the simpler form of the geodesic equation and solve it. Because once you solve it, you will get a straight line which will automatically be finely parameterized. So that's how it goes. Now what do? Should we stop here? तो कल भी हम फिर थोड़ी सी लंबी 2 घंटे की कल कर लेंगे. सिर्फ ऑनलाइन होगी या फिर आना यहाँ पे. I mean, I'm fine both ways.
थोड़ी जल्दी करेंगे क्योंकि 6 बजे तक दूसरी क्लास स्टार्ट हो जाएगी.
6 बजे दूसरी स्टार्ट हो जाएगी
वो जाना ठीक है
तो फिर इसको ऑनलाइन ही कर लेते ना.
3 बजे
3 बजे किसी का प्रॉब्लम होता है
तो प्रॉब्लम सॉल्व करने का
वो तो पहले कर लें.
पहले कर लें 3 बजे कर लें. अभी ये रमला की आवाज नहीं थी यहाँ पे. किसकी थी?
जी सर, मेरी आवाज़ से मैं रमला बात कर रही हूँ। मेरी जो क्लास होती थी 1 बजे, वो इस वीक नहीं है, तो
अच्छा,
हम
तो
उसको
3
जल्दी
बजे,
कर सकते हैं।
हाँ वो कह रही है 3 बजे कर लें, so let's do it at 3, or let's do it just online, or you want to do it here? I'll come here, so if you want we can do it here.